Okay, welcome to video one in our course ST4, where we're looking at linear correlation and regression and linear models. So in this part, we're going to talk about which models should we use and how linear regression is a reasonable place to start. Of course, when we're doing this, what we might typically do is be here having collected our data and designed our experiment, plotted our data to understand that a linear regression is appropriate to apply. So that's our mathematical model. We then analyze the data using that model, get feedback on maybe the error associated with that model, and refine it in some sort of way and iterate this process several times until we are happy with our results, that they're informative for a particular question of interest. So when we're thinking about correlations and regressions, we can think about how we can link together two different data sets based on a pattern of data points that they have, like the ones here for sharks and tornadoes. They see to the extent to which they coincide, and that gives us a sense of their correlation. So you can see here that sharknadoes are very, very common because of their high coincidence here. If we look then at other correlations, things like the number of people who become entangled by getting stuck in their spreadsheets in the US, and the consumption of cheese there between the years 2000 to 2009, we see that there's a very tight correlation there, suggesting that there's some sort of link. And similarly, if we look at the number of people who died by becoming entangled in their spreadsheets and the total revenue from skiing facilities, again, there's a very strong correlation there for the same time period, suggesting that there's links between the skiing facilities and big cheese to get people to get entangled in their spreadsheets. So, of course, correlation is not causation, and if we're detecting an effect, we have to identify what actually caused the effect and what was left there after the effect had already happened. An easy example of that is to think about sunshine and the behaviors that we might have, such as increased consumption of cold foods and also things like sunburn. And these are correlated, but they're actually independent. So we give a separate item here causing these two different factors that are therefore correlated, but they're actually independent of each other. And classic XKCD cartoon on this is the person says, I used to think correlation implies causation. Then I took a stats class. Now I don't. Sounds like the class helped. Well, maybe. So we have to be critical about what we're looking at. So if we look about this kind of spread of data points, and maybe there's a correlation line plotted through it with a low or squared value, we have to think of whether we could actually just draw a random symbol to, in those points to consider if there's actually any meaning to it. And maybe there's artifacts in our data that give rise to particular patterns. And maybe simply we may have the answer is simply that there is no pattern, that there's no link between two different variables that might be of interest to us. In the classes themselves, we'll look at we use this website, Guess the Correlation, where you can look at a correlation and guess its R value and see how close you are from the true value here. In the same way, we'll use this website called rpsychologist.com, where it's a nice plot where you can adjust the points on this correlation graph and look at the correlation and the shared variance, and also the linear model of that linkage, showing the intercept here, 81, which is down here. The slope is 0.2. The mean of X and Y are about 101 each of them, so that's here and here. And they show the standard deviations as well, which you can see is lower for Y and higher for X. And you see how the shared variance, the covariance of X and Y and correlation are closely linked. So we have to think about what model are we applying and what assumptions do we have for that model about our model and our data. What structure should a model have? How sensitive is it to small changes in that model? What effects would those have? We have to consider if those parameters being used are realistic, are they tried, are the default parameters, where they come from, are they based in literature or other experiments? And then can the model be used to make predictions about your observed data that are tested then in new independent data that are separate from our existing experiments? So there might be published data, for example, that we could test. So if we're going to make predictions, how can we test that? So if you're in a position where you just cleaned your data, what's next? Well, linear modeling is a good place to start in essence. So there are different model selection approaches that based on things like goodness of fit, deviance measures, penalized deviance measures, information criteria, leaving out cross-validation, and so on. But linear model is a decent place to start. There can be very advanced models that might be nested or multi-level or multimodal. Um, but in a starting point is always to think about a linear association between two variables. Is a reasonable place to start to explore what's going on, and then we look at the error between the model prediction and the actual observed point where we're trying to predict the value for y here based on the estimate for x. We can have positive correlations and also negative correlations. However, this linear model is maybe a less biased model than compared to something that's a complex polynomial that in theory has a better fit. You can imagine if you have new data put into this model, it's not going to fit like this one here. So this model is not useful because it's overfitted. Whereas this model, it might fit if we have new data. It might actually work to a reasonable extent, actually therefore be useful. So we have to consider then that we want a model that we can understand, and that's the danger then of using back-to-box approaches. We think, oh, can we just automate everything? But in reality, it's not that simple. So there's different approaches to that can be used. But in the context of biology, often what we want to know is how are they correlated and why are they correlated? And therefore, the black box is not necessarily helpful for us if it doesn't tell us about the mechanism at hand. So we might want to know what variables are causing this association between these two different phenomena. So if those black box approaches will tell us about that, then that's great. If not, then that might not be actually useful. And the example of this for Episystems in the USA, which use artificial intelligence to identify sepsis in particular and the associated hospital stay lengths. The issue with that is that it was misleading about the prediction power that it had. So Episystems, they looked at 28,000 patients or so with 2,500 cases of sepsis. And they had, in this subsequent study, they found that there was a receiver operating characteristic curve of 0.63, which, if you know anything about these curves, is pretty low. And importantly, they only detected 7% of the patients that did not get their antibiotic quickly enough, because if your sepsis time is is very, very important, and it's not necessarily easy to diagnose either. What is worth noting as well that it identified 6,000 false positive cases of sepsis, suggesting that its specificity and sensitivity are very, very poor, and then also its false negatives at 1.7K of them too. So in the initial study, it had reported a ROC curve of around 0.7. However, in the subsequent study, a follow-up, it showed actually it was lower. And you can see here with the PVV, so remember that's the true positives divided by the false positives plus the true positives. You can see there that that is very low compared to what you might hope for. See here, this for the different models for thresholds, that is, it's quite on the low side. So again, we have to go back to our model ideas, and then are we correlating, inferring causality for two different independent variables, and what should our model be? And if we're thinking about protein-protein binding interactions or DNA regulatory networks or some other complex model, we have to think about what we can observe. We also have to think about what we're not observing too. So if we have a more complex model where we're not observing things, how will that affect our model? That's very important. And we also think that there might be more other versions of models that we're not actually considering that might be present inside here. So causality and correlation are known subjects, and we have to think about what is our model that we're using here, and what is our model in terms of the complexity of different factors that might cause the effects that we're observing. So that's the end of video 1. Please see the next video on correlation and covariance.